Hi everyone, today we will be talking about the polynomial regression. As you remember, the last video is about linear regression with linear algebra. We will approach polynomial regression solution with linear algebra view, and we will do the same idea with the linear regression for polynomial regression. Let's then review the linear regression and its ideas, and then talk about the difference between polynomial regression, and then talk about the how do we implement it. So in linear regression with linear algebra solution, we have some data set, and we have added randomness on it, and then we try to fit a linear try to fit a line that minimizes the distance between points and this line. So we try to minimize the total sum of the distances between these points and line. So we sum it and then we try to minimize it. This is the idea. But a line consists of slope and intercept. But in polynomial regression, we will have an equation like this. So it has more degrees than the linear regression. So what we will change is actually the matrices that we define. So in the earlier case, in the linear regression case, as you remember, we have two matrices for multiplication, and we actually did it by numpy dot x multiplied by b, or x dot b. So we can say that the idea is the same. So we will do the same matrix multiplication, but we will add some dimensions to the X dataset and then B dataset or B array. So in linear regression, we have two distinct parameters in X array. As you can see, it's one column has ones and the other column has the different values of X. And these are the corresponding values for X multiplied by b1 plus b0. The idea is simple. 1 multiplied by b0 plus x1 multiplied by b1 is equal to y1. And then we add the randomness to it. The idea is the same. But as you remember, in this example we have we need x1 and 1, because b0 has 1 as a coefficient, and x1 has b1 as a coefficient. So in polynomial regression, we have an equation like, let's say, we have 2 degree polynomial, 1 multiplied by b0 plus b1 multiplied by x1 plus b2 multiplied by x2 squared, x1 squared. So we need to square the matrix. So to have an equation like this in a matrix form, in a matrix multiplication form, we will add two things. The first one is adding b2 below the b1 as a coefficient, as a new coefficient, and also we need to stack x1 squared to the right side of the x here. So if it's 2 degree polynomial, we will add 2. If it's third degree polynomial, we will add 2 and 3, and also it will go on like this. So for the optimization parts, let's review it quickly. But if you want a deep review on it, you can click this video, or you can check the optimization idea here. But the idea is the difference between the original dataset and our prediction is this, or we can say that the difference between the distance between prediction and the real values. We need to square it, and then we need to optimize it according to this b. So if we take the gradient with respect to b, and let's say that it's equal to 0, we set this equal to 0, and we try to solve it in a linear algebraic way, we will say that the original B matrix, which means that our our prediction matrix is optimal prediction matrix is x transpose x inverse x transpose y. So this is the solution for that. So this is B is in this form. So we will do the same thing. We will do the same, exactly same optimization idea for polynomial regression. What we will change is we will define, we will create an artificial data set in a different way, and then we will need to create a matrix like this, and also we need to then fit it. The respect is the same. So let's code it, and while coding it, we will see some. We will observe some realities about the polynomial regression. So this is the spoiler part of it, and let's import numpy of import numpy is np, and let's import numpy dot linear algebra for the inverse operation. We will use it. Import linear algebra as lng, and import matplotlib for the graphs. So let's create the data set. I want to have a data set that is between minus 10 and 10, and let's reshape it to this form. Why not 1? This is because numpy expects something different, so I don't want to explain and confuse you with this, but it's not a big deal. So let's talk about the Van der Monde matrix first. So the Van der Monde matrix is, if you have, let's say that, forget about here, if you have, if you want to create a data set, create an input data set for 2-degree polynomial, as we talked before, you will square, you will need a matrix that has one arrays on the left, and then first degree of the data set, and then second degree of the data set, and then nth degree of the data set. So this is called Van der Monde matrix. Basically, what we want to see is we need to have a Van der Monde matrix for our matrix multiplication, and then we want it to have fourth degree, because we need to apply this formula. We will try our polynomial regression algorithm on this formula, on this equation actually. So why, if it's the fourth degree, why it's the 5? Because this is the shape of the columns, or number of the columns in this matrix. So let's print it, you will get the idea. The first column is preserved for 1 arrays, and let's say that this is increasing in an increasing order. So the first column is preserved for 1 arrays, and the second is x1, third is x1 squared, 4 is x1 over 3, fifth is x1 over 4. So this is the idea of Van der Monde matrix. And then we need to have to create an artificial data set, we need to have some parameters, and what we will have is actually this graph you can see here, and you will fit a polynomial on it, and it will have shape like this. And to simulate that, we will use the parameters in here. So let's say that y is equal to numpy dot x. Let's say that this is the original numpy array. We will define the coefficients of this matrix, but we will start from here. 6 minus 2 minus 12 plus 2 and 1. So this is our original B matrix, and if we multiply it by original B matrix, and let's say that we shape it to the 1 and 20 again, and we will see a result like this. You will see a result like this. And let's say that we want to plot it. plt.plot numpy arrange minus 10, 10, 1, and then we need to plot y and then show it. When we run it, we see that it has a shape like this. Okay, so it's kind of similar, but if you want to see this graph, let me get closer to it. You see, this has the nearly same shape, and probably this is kind of manipulated a little bit, or numpy, sorry, matplotlib has, okay, so it gets similar and similar when I'm close, right? So sorry for blaming. And this is the original data set, but I want to add some randomness on it, because if I apply the polynomial regression with the same data set, I will have nearly same parameters for this matrix, and we will observe that also. So let's say that our random data set is created by random normal. Let's say that mean is 0 and standard deviation is 50, and the shape of the matrix is 20 by 1, or 20, let's say. And let's see the difference between original data set and what happens if we apply randomness on it. So this one is the original one, and this one is the data set that we created artificially, and it has some randomness parameter. And let's increase the randomness like this. So we will see we have some errors here. Let's run it again. Sorry. Let me close the video for now and continue after that. We just need to add one here, and then if we run it, we will see that the original data set is plotted, and this is the data set with dots is the artificially created data set. So this is we had a variance to the data set, so we had a randomness on it, but the plot shows the original data set here. So what if we increase the randomness on it, or let's say that increase the standard deviation? So this is the original data set, the plotted one, but the scattered one is the data set that we artificially created, and randomness that has a randomness on it. So let's adjust it to the size that has a little bit randomness or standard deviation. So let's delete this. This is our original data set. So we'll apply the same idea, right? So let's say that B is B artificial, let's say that this is B polynomial, and we will apply the same idea with the linear regression part. So we will apply x transpose x inverse x transpose y. So we have again a spoiler in here. So let's do it. We have nothing left to talk. So for the polynomial regression solution, we will apply x transpose x inverse x transpose y here. So let's first of all define x transpose dot x, numpy dot x transpose x, and let's inverse it. lng dot inverse. Let's inverse it, and let's also define here x transpose y here, numpy dot x transpose y, and then we need to also dot them together. So numpy dot x transpose x inverse x transpose y, and this is our polynomial solution here. Let's print it first. Okay, let's change them by y instead of y2. So this is the original dataset, but we didn't plot. We haven't plotted the original. The predictions. This is the original dataset. So you see that this is the parameters for polynomial regression. So what we see is the B matrix, B matrix in here. So, but it has 5 parameters instead of 2, because we are doing a 4th degree polynomial regression. And the original B matrix is this. So if we decrease the variance, we will see that we will get close to that point. 5, 1, 5, minus 1, minus 12. You see that we are getting closer and closer when we decrease the randomness on it. And we have some problems in here. I don't know what happened. Sorry. Let's say that we decrease it to the 1. So it will get closer and closer again. So what if we say that it is 0? You see it is exactly the same. So the optimization solution works very well. However, we want to see the polynomial result with the high variance, with applied on high variance. So let's plot it. plt.plot. So this is our prediction. plt.plot numpy range between -1 and 1, and our predictions are x and b polynomial solution. So when we show it, we will see that it really fits to the dataset. When we get closer, we see that we have some errors. However, that's a good solution. But I'm not talking about the polynomial regression solution here. What I mean is polynomial regression degree. I don't want to comment on that in this video. That is the topic of another videos. So if you increase the polynomial regression solution degree, what I mean is if instead of 4th degree polynomial you try to apply 7th degree polynomial, you will have a better solution. Maybe it will cost more in terms of time. However, that won't be beneficial for some cases, for actually lots of cases, because when you increase the polynomial regression degree, actually you are getting far from the generalization. This is just the idea. But before finishing the video, I just want to apply 3rd degree regression in this dataset, and probably we are done here. So when we run it, this is for another formula, but the variance is so high in here. Let's say that the variance is 5. So if we apply 2nd degree polynomial regression for another dataset, this is our solution. If you want to apply, let's say that's 8th degree polynomial regression on a dataset like this, I'm just now doing something that I don't know. It doesn't fit. I need to increase 1 probably and run it. We will see that it also works for 7th degree polynomial regression. So this is the idea. This is the solution of polynomial regression with linear algebra. For the backpropagations, I want to create a new series that we try to call neural network and convolutional neural networks, and I will publish it again in English language. and let's see you on the other videos. Thank you for watching.